Hi, my name is Gene. I'm a new mentor from high school robotics team FRC 714 from Newark, New Jersey. And probably the reason you're watching these videos is you want to transition your students from an old language, Java, to a language that's used in a lot of modern applications, Python. And because if you look at the job market, they will graduate in a few years, and there will be even more AI-based technologies around, whether they become software engineers or some other engineers or not engineers at all. They will probably want to use those AI technologies or products, and very often the most convenient way to do this is by doing it through Python. So that's why it's a good idea to learn Python by doing FRC. Why not? Today we're going to look to write a code for probably the most dangerous subsystem that exists in FRC robots. We're going to write Python code for a robotic arm. Problem with the robotic arms is that the modern motors are so dangerous, so powerful these days that if you're not careful with your code, you can break the arm, and limit switches will not stop this, but you can also possibly injure a real person or hit a real person. So if you are not feeling 100% confident today, if your mind is not 100% clear, maybe you're stressed, maybe you're sleep deprived, maybe something else, you can write the code, you can test it in simulation, but do not test robotic arms in reality if you're not 100% confident, if your mind is not 100% clear. Sleep, drink water, and maybe test a robotic arm tomorrow. If you don't trust yourself to drive a car, definitely do not trust yourself to test a robotic arm on such a day, a new robotic arm. Did they just scare everyone? Well, the reality is a little complicated. For example, we're not scared to walk into a bus or into a train, because they have already been built and tested, so they're safe. Same here. If you write your ARM code and test your ARM code to be safe, then you can use it from there on, because it's safe. But when you're doing something untested, for example, new ARM code, or maybe building a new train or a new bus, then you have to test it really well, because it can be quite dangerous. So with that, what we're going to do is we're going to take the robot from the previous example, from the previous video. So same link in the description. Swerve Drive, Rev Swerve Drive robot. We're going to its GitHub webpage. And at the bottom, if you scroll all the way to the bottom, you will see that there is some documentation about adding other things to this robot. I have posted some code snippets for how to easily add an arm to a robot. This robot, that robot, some robot, how to add an arm. It's an example, it's a simple example. I'm going to click on this simple example. Here we have a code snippet for adding an arm to the robot. There are some warnings, so yes, first of all, we will need to check that the motor directions are correct and sensor directions are correct, and we will see it later in this video how I'm doing this. It is important to start with very small values of proportional control coefficients, so that the arm doesn't just explode and, hit it, break itself, or hope, God forbid, hit somebody. Those proportional control coefficients, P and D, will need to be tuned to your robot. The values that I have in this example will not necessarily work with your robot. You have to just follow the same process that I'm going to show later in this video in order to come up with good P and good D coefficients that are good for your robot gear ratio, your robot mass, your own robot. And you might need to assign different addresses to the motors if the addresses which are used here are already taken. So without further talk, this is the code snippet for the arm. And for convenience, I added the arm constants class in here. You're totally fine to move it into constants.py. But what I'm going to do is I'm just going to copy this whole code snippet. And let's see, supposedly it needs to go into subsystems. slash arm.py. Let's do exactly that. I go to my PyCharm. I go to my project. I go to the subsystems folder, and I'm going to add a new file, just like mentioned in there. I'm going to call it arm.py, like this. And then I'm going to paste that whole code snippet into here. No big warnings, so I think it looks fine. Okay, a small warning about blank lines. Well, will go away. And apparently, yes, other things we will address. Next up is after we add the code for the arm, we need to add this arm to the robot itself. How are we going to do this? Inside of robot container.py, there is this init method. Very often we call it a constructor. This is something that, this is the function that runs when we construct a new robot container. So what we need to do is inside of that init function, we'll need to add an arm. We need to add one arm. So let's go to robotcontainer.py and let's find the constructor. Let's find the init function. Here, I found it. There it is. So right in the front where it says the robot subsystems, I'm going to add another subsystem, an arm, here. Now, the arm is highlighted in red. Why is it highlighted in red? Because inside of robot container, we didn't say what arm is. We need to import the arm from subsystems.arm. This is how you do it. The snippet is here at the bottom. So all we have to do is wherever we import things, we need to add the import for the arm, just like this. Finally, CAN IDs. So apparently there are ARM has two motors, ARM motor right and ARM motor left. And we need to add them as CAN IDs. What are we going to do? How about we add another set of constants, CAN IDs, into constants.py in here. Right after we have drive constants, or right before the drive constants, wherever we have all the CAN IDs for the motors here, we can add another class CAN IDs. And we can mention both arms in it. Arm motor right and arm motor left. Arm motor right, I think, is 12, and arm motor left is 13 on this robot. So I went to the robot and checked. Apparently the address of the right motor, the CAN ID, is 13, and of the left motor is 12. So this is what they should be. Now look at your robot. Maybe on your robot they're different also. Maybe one is 9 and another is 14. You have to check. You really have to check. Let's now go and see if it's complaining. No, it's not complaining. So the ARM subsystem is kind of added. But it's not used at all until we make this ARM do something. For example, we can configure a button. And so, inside of this adding ARM documentation, we have another code snippet that we're supposed to put inside of configure button bindings function. This function defines which joystick button does what normally. Normally, you want this function to define this. So we're going to say that the A button of the joystick, when A button is pressed on true, we're going to do an instant command in which we say arm dot set angle goal to be the minimum arm angle. I think that's 14 degrees or something, basically all the way at the floor. And the Y button, which is the button that has key of KY. For the Y button, we're going to attach another command. We're going to say, when Y button on pressed, on true, run another instant command in which we say arm dot set angle goal 70. When the Y button is pressed, set the desired angle of the arm to 70. I let the motors drive it to 70 degrees. So I'm going to copy all of this and I'm going to put it into my configure button bindings function. Look at this, it's completely empty. So now we can put something into it. Configure button bindings function is done. And I think it will work. What we can do is we can switch to testing and simulation and running the simulation. Before we deploy the code to the real robot, it's always a good idea to test in simulation. Simulation, especially this simulation that I have here, will not discover all the problems with the code or with the systems, but it will discover some, and hopefully we can fix them before breaking anything real. So I switch to sim and I hit run or debug. You can hit debug also. I'm just gonna hit run. So here we have our simplified simulation. We already have one of the joysticks in here. So we can add another joystick by dragging the second Xbox controller to here. Okay, I'm sorry, maybe this one. Now we have two joysticks. So if I move my joystick buttons, the simulation senses this. I'm going to switch to the teleoperated mode, and I'm going to look at the output in here, output of the program, to see if there are any errors. I'm going to now switch robot to the teleoperated mode, and I'm going to try to lift the arm up, down, up, down. So nothing bad seems to be happening. What we can also do is we can make it very explicit. We can go to the ARM code and do what is called breadcrumbs, which is you print something out that you want to see. For example, I'm going to print the angle goal that the arm is given. And we will try to repeat the experiment. So now this code will be simulated. And I'm switching the robot to teleoperated mode. And on my joystick, I'm going to be pressing the arm up button. And you can see, I see the printout, set angle goal 70. I'm pressing the arm down button. And on my screen, I see set angle goal 15. So the code is definitely doing something. We don't know what it will do to the actual motor, but at least the joystick control works. And also nothing crashes, nothing breaks in terms of exceptions or errors in the code. We're ready to deploy it to the real robot and to test there. So I'm going to stop it. I'm going to switch it to the deploy configuration, and I'm going to run the deploy configuration. Don't forget that we need to connect to the what are we going to connect? We're going to connect to the robot network here. So the robot is up. Moment. Go. Robot network is 8630. Now I should be able to deploy this code to the robot by running the deploy configuration. There we go. Down on the bottom here it says, in case you cannot see, I'm moving it. It says deploy was successful. Now, it is actually very important to, when you start testing a new arm on a new robot, to keep things very safe. Let me show you what I mean. We need to go to the arm constants, and we need to completely get rid of the D term, like this. We're going to multiply it by 0. And we're going to use a much, much smaller value for the P term, proportional term, because what if these constants are incorrect? We don't want the arm to break itself, and we definitely do not want the arm to injure someone. So I'm setting it to a very low value. I'm setting D to complete 0, and I'm setting the P, proportional control coefficient, to 0.05 of what it was in the example, just to be on the safe side. And I'm hitting deploy again. Deployed successfully, we can now go to the robot and start testing with very, very small coefficient. Okay, so hopefully you guys can see what's happening. Here I have the robot sitting on the floor. I have this rubber rug under its arm in case the arm tries to slam the floor and break itself. And one thing I need to show you first is how to do an emergency stop. If the robot gets out of control, you can always do an emergency stop by hitting enter. So I'm going to enable the robot until operated. And let's just say, oh, it's out of control, as you can see. So keep your hand on an enter button in case you need to stop the robot, in case something is going out of control during the test. And this is ARM. ARMs are dangerous. Uh, what we're going to do first during this test is we're going to ensure that the directions of the angle sensor is correct. I have set my P, a proportional control number, to a very low value, 5% of what it was in the example at first, and maybe 5% is still too much, but we shall see. Um, I'm going to enable, and I'm going to press the arm up button. It sets the angle goal to 15, as you can see in the printout in here, coming from the robot, from the log. I'm setting the arm up button again, and I see it's doing a slight push in the upward direction to my hand. I'm going to push the arm down button. It's doing a slight pull down on my hand, but it's not strong enough to actually lift the arm itself because we have set the P to a very low value. So at least this way I know, okay, the direction of the angle sensor is clear because when I want the arm to go up by pushing the arm up button on the joystick, it's kind of trying to pull up a little on my hand. It's not strong enough to even lift itself. And arm down, it wants to go down. So this is great. The directions are correct, and now we can start finding the right coefficients. WPI actually recommends using a more industrial procedure for this than I'm going to do. But what I'm going to show you, you can always do. And actually, a lot of engineers in their real work do what I do right now. So don't look too badly on me. I'm going to start doubling the P coefficient and redeploying the code. So it was 0.05, now it's going to be 0.1 times the value in the example. Code redeployed. Fantastic. Code redeployed, robot restarted, enable. Now I'm still going to hold it with my hand and be prepared to hit enter on the keyboard anytime I want to. But let's bring the arm up. Okay, it's still it kind of can't hold its weight with this value of P, but it's still going down. Now if I push the arm down, it goes down faster. And you can see it in here. Okay, let's double the value of P again. Now it's going to be 0.2 instead of 0.1. And for the reasons we're not going to discuss, you must keep doubling it. You cannot like tripling or quadrupling. It's the safest way to do this is doubling. So I'm going to deploy a robot code again with 0.2. And let's see if 0.2 makes the arm a little stronger. The proportional coefficient, proportional gain as they call, of 0.2 makes the arm stronger. I'm enabling the arm and I'm pushing the arm up button. Oh, now it can hold its weight. Now it's not falling down, or almost not falling down. Anyway, so and if I push the arm down button, angle goal of 15, the arm goes down. Okay, this is a step in the right direction. Let's double it again, 0.4. And deploy the code again. Arm the robot in teleoperated mode again. And let's do arm up. So now with a 0.4 coefficient, the arm can move up, but perhaps a little slowly. And when I push the arm down button, it can go down, but also perhaps a little slowly. What we can do right now is we can double it further, make it times 0.8. and deploy again. Do not increase it by more than a factor of 2. This is not safe. We need to keep increasing by a factor of 2. You will see why. Arm enabled, arm up. Okay, that's faster. That's great, right? Arm down, works. And it does not break the floor because I have said don't slam equals true in the code. Feel free to read it. It's a little bit more advanced. Imagine I actually want to keep doubling it because I want the arm to go up real fast. I will show you what happens if you double it too much. We're gonna do it safely. Deploy the code with 1.6, with a P coefficient of 1.6. Code is deployed. Let's enable the... Okay, it needs to restart. Robot is restarting the code. Now I'm going to enable and bring the arm up. That was fast, right? That was bad because it's slamming the floor, so we'll need to make some further adjustments. But it's going up pretty fast. Now, in order to prevent slamming and overshooting, what we need to do is we need to add a D term. You probably already saw in the code that there was a to 0. We did not bring the P term so high up that it's just shaking out of control and doing explosive oscillations. This is what you don't want to do. You can do a little bit of this, but you have to do an emergency stop. But now it is time to do the D term, which you can call dampening term. I'm going to set the D term to, for example, 0.1. We also need to be a little bit careful here. So I'm going to deploy the code again. D term makes the arm slow down as it approaches its final destination. Slow down a little more. So arm up and arm down. Slam again, right? So I keep doubling the D term. I don't have to slam the floor each time, but it's important to be conservative with how you increase those things. Enabled. So now the arm does not overshoot anymore, or doesn't overshoot as much when it goes up. But I want to keep in mind that arm does not overshoot at all. So I'm going to set it to 0.4, deploy, and try again. The code is deployed, robot is enabled, arm is going up, and I hope it doesn't overshoot about the point where it needs to be. Oh, it's still overshot. I'll be honest. Bringing it down, and it still slams. But I hear the vibration caused by the D term already in the motor controller. So I'm not going to increase the D term anymore. Instead, I'm actually going to bring down the P term to the level that doesn't cause the arm to slam on the floor. And deploy the code from here. When the D term is too high, you will hear it is caused by motor controller slightly over controlling that motor. So now the P is set to 1. I'm going to bring the arm up. The arm does not overshoot. There is a little bit of this vibration noise still, but it's manageable. And I'm going to push the arm down button. The arm went down pretty quickly, but it did not slam on the floor. It stopped right before. So I kind of like this value of P, 0.1, and D of 0.3 times whatever I had in the example already calibrated. I'm going to keep them this way. And with that, the arm calibration is finished. Yes, so please trust me, you will actually not stop there. You will keep experimenting, you will keep making fine adjustments to the coefficients because it's fun to play after you have established what's safe. So after playing a little bit more, I have established that I like the d of 0.2 a little bit more than d of 0.3. And this is where we're going to stay. Thanks for watching. So today we have added an ARM code to a robot that had an arm. How we did it? We went to this repository, command rev swerve, which is for swerve robot, but the arm can be added exactly the same way to a tank robot or a submarine robot maybe, because the arm doesn't really change. Scroll to the bottom of the main page of this repository. There are links how to add an arm and how to add a camera. I clicked on that link and we followed that instruction to just add the arm to the robot, and everything worked. Thanks for watching, and next up we will do the same, but we'll be adding a camera. Stay tuned.